All right, so here we go. Some more examples of what we're looking at here. We're looking at more examples of permutations. Okay. A softball team has 18 players. How many unique 9-player batting orders can be created? All right. So I have a set of 18 things. I want to make a subset of 9 of them. The order matters. And I can't repeat, meaning I can't have the same person batting twice in the same order. That right there is the definition of a permutation. That you have a fixed set of items, you want to make a subset, the order matters, and you're not allowed to repeat. So this is going to be a permutation of 18, taking 9 at a time. And so there's a formula for that, but I'm just going to use my calculator. 18 permutation 9. What does that mean? Oh, E10. Scientific notation. So that's 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's see, that's hundreds, thousands, millions, 17,643,225,600 ways to make a 9-player batting order from an 18-player team. This right here is what Chapter 8 is about. We want to do something, but the thing we want to do is so big there's no way to count it up, to list it out, to draw a tree diagram. Not going to happen. So we need more math. Okay? A local chess club has 36 members. So I have a set of 36. In how many ways can a president, a vice president, and a treasurer be elected? So I'm making a subset. I'm picking 3. Does the order matter? Well, if you're picked to be president, is that the same as being picked to be vice president? Okay. So the order matters. So that's good. And we can't repeat because you can't be 2 of those at the same time. So since we can't repeat, and I spelled repeat with an extra E, then we know that we're making a permutation. So this is going to be a permutation of 36. Choose 3. Okay? So once again, grab my calculator, 36, math, number, probability, NPR, NPR3, and I get there are 42,840 ways to select a president, a vice president, and a treasurer. Okay? Distinguishable permutations. Suppose you have n elements in a permutation, and there are n sub 1 elements of type 1, n sub 2 elements of type 2, and so on for r different types. And the number of distinguishable permutations is n factorial divided by n1, n2, n3, n4, n5 factorials all multiplied together. What does that even mean? Well, in the examples we looked at, we were creating a subset each time, but the items in the original set were distinguishable. What I mean by that is, I can tell all 36 members of the chess club apart, or I can tell all 18 players on the team apart. But what if I have an urn, and in that urn there are 3 red marbles, and I can't tell those 3 red marbles apart? And there are 5 yellow marbles, and I can't tell those apart. And there are 4 green marbles, and I can't tell those marbles apart. And there are 7 orange marbles, and I can't tell those marbles apart. So if I make an ordering, if I make a subset of those that goes red, red, yellow, is that different from red, red, yellow? And you're going to be looking going, what do you mean? Well, if I switch these two red marbles, are those different permutations? And the idea here is, if I can't distinguish between those two, then they're the same permutation, right? So what we're talking about here is if you have a set, in this case we have a set of, and there are 3 and 5 and 4 and 7, so that's 19 marbles. But within that set, there are chunks or subsets where you can't tell them apart. So then I have n sub 1 would be 3 red marbles I can't tell apart. And n sub 2 would be 5 yellow marbles I can't tell apart. And n sub 3 would be 4 green marbles I can't tell apart. And n sub 4 would be the 7 orange marbles I can't tell apart. Then if I want to order all those marbles, all those elements, the number of ways that I can do it is going to be 19 factorial divided by 3 factorial times 5 factorial times 4 factorial times 7 factorial. Now I can either do this by hand or I can type that as it is in the calculator. I'll show you both. If I was going to do that by hand, it would look like this. 19 times 18 times 17 times 16 times 15 times 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1 times 5 times 4 times 3 times 2 times 1 times 4 times 3 times 2 times 1 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then I would start doing a bunch of cancellation because 7, 6, 5, 4, 3, 2, 1 is going to cancel with 7, 6, 5, 4, 3, 2, 1. 4 times 2 is an 8. I got a 3 times a 3, that's a 9. Let's see, what else can I get rid of? I got a 5 times a 2, that's a 10. I'll take this 3 and this 2, make that a 6 and make that a 2. Everything's gone from downstairs, so I just need to multiply the upstairs. So I've got, what do I have left in that numerator? I have 19 times 18 times 17 times 16 times 15 times 14 times 13 times 2 times 11. If I did all that simplification, or that big number right there. 5, 5, 8, 7, 0, 2, 1, 4, 4, 0. So 5,587,021,440. Or the easier way to do this would be just to take it like this and put it into the calculator. So I'm going to make a fraction. My numerator is going to be 19, and I'm going to go to that same place I've been going and see option number 4 there, the exclamation point, 19 factorial divided by 3 factorial times 5 factorial times 4 factorial times 7, what's the 7? Factorial. Oops. 19 factorial over 3 times 5 times 4 times 7 factorial. That number should be the same as that other number. I must have screwed up somewhere. Where did I screw up in my math? I don't like when I make mistakes. Something about doing that math must have messed up. There's the 7, 6, 5, 4, 3, 2, 1. There's the 7, 6, 5, 4, 3, 2, 1. 4 and 3 is 8. 3 and 3 was the 9. Ah, see that? I never got rid of that 4 downstairs. So I got to take this number and divide it by 4. Ah, there's my mistake. So let's go grab that number. Divide that by 4. And there, then they match. Okay, found my mistake. Now I want to just point out something about that mistake I just made. I'm good with numbers, and I made a mistake trying to write this thing out, trying to do all this right here. Okay? Don't do that. Take it straight to the calculator. Type it in. Get the answer. Okay? These things are a bear to do by hand. Use the technology. All right. That is the end of section 8.1. The title of section 8.1 was about permutations and multiplication principle. Our job was to pick up some new skills on how to count up how many things there are. So one way was the multiplication principle. If you have steps in your experiment and there are a known number of ways on each step, multiply them together. It'll get you where you need to go to. If you need to make subsets, if you need to make ordered subsets where there's no repetition allowed, right? It's a permutation. Now there is a formula, again, but we're not really going to use it. We're going to do these things with the calculator. We're going to push the buttons. So the permutations on the calculator, where are those hidden? Math, PRB, the probability menu, it's option number 2 there, okay? It's that PRB menu. Same thing with the distinguishable. Now, even though there's a formula and you can try to do these things by hand, I don't recommend it. Okay? I highly recommend just taking the formula, sticking the formula in the calculator and grinding it out that way. All right? I'm going to end this video here and we'll come back, and next time I see you will be in section 8.2.